Last speaker from this group is Eden Yemasegan, and she is from, sorry, let me bring her on stage. So Eden is a PhD student at Penn State, and she has been looking into parametric studies of the direct energy deposition, DED, additive manufacturing, and quality control, GUI development. If she is ready to join the stage, she can turn her camera and mic on. Eden, are you there?
Yes, I'm here. Can you hear me?
Beautiful. Yes, we can. Thank you so much. Would you like to share your screen and bring up your presentation?
Sure. Great. Can you see my screen?
Now we can. If you do you want to click present mode, just so we're definitely getting the right. Yes, perfect.
Right.
I will leave you to it. Thank you so much, Eden.
All right, thank you. Thank you everyone for joining. I'm pretty excited for this presentation. It is one of my great research work on metal 3D printing. So just a little bit about myself. So the title of the presentation is Parametric Studies of Direct Energy Deposition, Additive Manufacturing, and Quality Controlling GUI, Graphical User Interface Development. My advisor is Dr. Alimi Mari at Penn State, but I also work on this project in South Korea, where I studied my master's degree at KAIST. Just a little bit about myself. I love traveling. I travel to different places to study my graduate degree. I was born and raised in Ethiopia. That's where I studied my undergrad. But I traveled to South Korea, China, and Japan to study my master's. Well, in a break, I also work at different companies working on consultation and in the construction field. I also went to Burundi for some projects, and currently I'm here in the US at Penn State University studying my PhD in Architectural Engineering department. My engineering journey started from 2013, actually, when I was joining my undergrad. But I learned about 3D printing since 2019. I learned about metal 3D printing, and then through that, I fell in love with the application of 3D printing, how it can simplify things in the manufacturing industry. So I studied both metal 3D printing and concrete 3D printing in my graduate study journey. Today, I will give you a little bit about presentation. I'll start with the introduction and continue with the research development, why I selected this topic and its importance. I have also done some experimental works, so I will share you my experimental works, including their results. So my main goal in this research is to study the parametric values of the DED 3D printing. So I also will discuss about that. I also have developed a graphical user interface in this research. I will share you that, and I'll go to the conclusion. And if you have any question, please feel free to shoot a message on the chat tab. So I start with what kind of challenge do we have in 3D printing? So in 3D printing, we have the original CAD model that we have developed, and then we'll have the final 3D printed product. And if you literally measure the geometry of the original CAD model with the 3D printed product, you will see geometric discrepancy, and that's due to layer height and layer widths. So, even though that, additive manufacturing has a very huge advantage in terms of in the aerospace industry or in the biomedical industry, this geometric discrepancy has huge problem. So, how can we solve that? How can we assure the quality of the final printed product in terms of size or geometry? And in this research, I use two basic key phrases. These are as designed object and as built object. So as designed object is the modeled object in the modeling software, in the CAD software. And as built object is the final printed object using this 3D printer or any kind of AM technology. So then the solution to the geometric discrepancy challenge is either to monitor your printing process offline and give feedback control, or monitor it online layer by layer and get feedback control. So when you're monitoring your 3D printing process offline, that means you're controlling it after the printing process. And if you see any geometric discrepancy after the printing process, you need to repeat that. You can definitely change some of the parameters on the printer, but you will face the you'll face like the wastage of material, wastage of time. So why not controlling that during like the printing process? That's like during real time. There are various research developed studying offline profile monitoring and online layer by layer monitoring. In these methods, they use various monitoring technique where they can scan the printed product using a laser line scanner. They use some kind of ultrasound. They use like a thermostat instrument. But in my case, the focus of my research is to focus on the DED, direct energy deposition, because there are various additive manufacturing technology. It could be a concrete 3D printing, marble 3D printing, wood 3D printing, organ 3D printing, and the machines could be, powder bed fusion, direct energy deposition, and a lot more. So to kind of narrow down my parameters and unknown values, I kind of only focus on direct energy deposition, and that was also the machine available in my lab. And to kind of monitor and scan the geometry of the printed product, I use a geometry monitoring equipment, which is a laser line scanner. And well, my methodology is online monitoring or real-time monitoring. So the objective of this research is to explicitly understand the effect of process parameters in the ED using a laser line scanner to help me develop a quality control graphical user interface for real-time 3D printing process. So once I understood that what kind of process parameters I need to improve during the printing process to assure that I'll have the expected geometry of my specimen, then I can provide a graphical user interface or a software that can integrate both the DED machine, the laser line scanner, and also your simulation software. So that's also one of the uniqueness of my research. This software kind of connects the DED, the laser line scanner, and the plotting or the simulation profile. It also will give you real-time plotting of the 3D printed specimens, and it will give you geometry discrepancy comparison of the printed specimen with the original CAD model. So basically, after the laser line scanner keeps scanning the frame points of the printed product, it can send that information on real time to the simulating software, and then it can overlay the scanned frame points on the original CAD model to see the geometric variation. So the research development, I have this general overview overview of my proposed methodology. So I do have 5 basic modules. It starts with the design module, go to the printing module, and the scanning, processing, and plotting module. On the design module, basically it's just developing the CAD model and then generating the G-code file so that we can send it to the printer. And once we upload that file in the printer, which in my case the DD machine, we can then initialize the process parameters to understand which can trigger the geometric discrepancy. Then before starting the DED printing, we should also trigger and send the signal to the scanning module and make sure that it's on the correct timestamp to collect the printed data. So once the printing starts, the scanning process also will start. So as you can see, this is the nozzle, and the scanner is like just a little bit behind that. Of course, there is a time delay, but we will achieve like very good results on that, and I will discuss that on the results section. And the processing module will match the as built and as designed data and extract the as built deposition. And finally, like we'll tell you, you know, this is the geometric discrepancy, and then those are the problems. So then on the GUI design, we can send a feedback control system based on the problem. So the experimental work, this is the setup, my experimental setup in form of like illustration. So this is the 3D printer nozzle holder. Behind that, there's this nozzle, the laser line scanner attached on the top of the nozzle. And then this is the orientation of XYZ. The printing passes in the X direction. So once like the printer is moving, the laser line scanner keeps also moving. And there's a 20 millimeter distance difference. And I'll discuss why later on, but then it'll be, this is the printed line. And we print it on some kind of specimen on the DED printing process. So for the machine operation, I usually check the temperature, switch off the power, usually calibrate the powder. I save the coordinates, I load the G code or the NC code. I run the 3D printing process. I also open and run the scanner and follow up the print until it finishes, and I'll remove the specimen. And for the laser line scanner, it uses the principle of triangulation. It has a CMOS array, CMOS array, and it has a light source. It has a receiver. So once like the laser arrays are penetrated on the specimen, it will receive like the frame points for each data set. And we already have our target set up. In this laser line scanner specifically has the ability to detect surface defects. It has the ability to measure height and depth, ability to measure the angle, but in my case, my focus is to measure the height and depth of the printed structure. So when using the laser line scanner, I definitely like set up the basic parameters correctly. For example, exposure time and saturation rate are the basic parameters in the laser line scanner. So exposure time is like, just like, you know, when you're using a camera, it's just the shutter time, or the time span for which a sensor is exposed to the light in order to record an image. So whenever like it's faster and whenever it's slower, it has its own quality discrepancy. So having that optimal value of exposure time is important. And of course, I get this optimal values through various experiments. And the same goes for saturation. It's the depth or intensity of the color present in an image. So having a very low saturation and a higher saturation will have an effect on the collected data. So the lower saturation has a muted color, so we might not be able to accurately get the correct widths of the printed profile. And whenever it's too bright, whenever it has a higher saturation, it'll be too bright, and the thickness will increase. The thickness of the printed specimen will increase. So the basic parameters in this study are process parameters, process signatures, and product qualities. There are plenty parameters that we can study in DED, but I choose laser beam, temperature, cooling rates, geometric irregularity, and also like some dilation. Each of this has their own correlation. So the process parameters, process signatures, and process qualities must be studied together. So in my case, like I kind of study both the qualitative and the quantitative correlation between the values that between the parameters that I selected. So the first parameter that I selected was exposure time, which is directly related to the saturation rate. So I use different exposure time, 0.5 millisecond, 2 millisecond, 5 millisecond, and 10 millisecond. For those, I do have different saturation values. And as you can see on the plot, for different values of the exposure time, there are different plots of the printed spaceman, and that's only for one line of the printed spaceman or one track line. So the recommended saturation level for the laser line scanner that I was using was from 70 to 90%, and to assure that, for 70 to 90% corresponds to 5 milliseconds. And as you can see in the image here, the 5 millisecond has the best option in terms of even visually, determine the roughness of the scanned profile. So qualitatively and quantitatively, I choose the exposure time to be 5 milliseconds as the optimal value. And the same goes for the distance between the laser and the nozzle. So earlier I told you, see the gap between the nozzle and the laser, the projected laser beam, is important. It should never be very close, should never be very far. So the way I obtain the optimal value for this is, of course, setting the exposure time to be fixed as 5 milliseconds, fixing the saturation, closing the door of the printer, and then varying the value of the distance between the laser line and the nozzle. So with 5 millimeter and 20 millimeter distance gap, I do have different plotted frames. And as you can see in the image, the 20 millimeter is the best option. For 5 millimeter, because it's very close, it's, because there's a laser coming from the nozzle, the DED nozzle, and there's also a laser coming from the beam. And if those two lasers touch, or there would be some kind of interference causing loss of data. So that's why 20 millimeter became the best option. And if it is greater than 20 millimeter, we wouldn't be able to collect any data. So that's the reason why I chose it to be the optimal value. And for light reflectivity, of course, again, setting the exposure time, the saturation, printer door, and distance between the laser and the nozzle, I played with maintaining and not maintaining the reflection of the printing process. In this case, when the light reflectivity is maintained, as you can see, the plotted profile is very smooth and can show almost all frame points. Whenever it's not maintained, there is some rough texture on the printed spaceman. So that could be due to the reflection, because the material I was using was stainless steel and it has its own reflection with the light. And the spread of powder, so you're using powder. I used a stainless steel powder, a metal powder. So that powder sprays everywhere, and that has also effect when scanning the printed profile. Of course, if I want to run online printing process, I wouldn't be able to clean the powder, but I just wanted to also play with this parameter and see if it has a very big difference. So whenever it's cleaned and not cleaned, the only thing that's different on the image that you can see is just the little bumps, which can be an overlay on the plot and can be avoided when plotting the geometry. So here, before the optimal parameter, the printed specimen, as you can see, has a little bit of noise, but after the optimal parameter are set, the noise has decreased and we can get a good image of the printed product. So then understanding all these optimal parameters, now I know how to set those parameters, and I developed the GUI, graphical user interface. This graphical user interface relates both the as designed module, as built module, the overlay module, and also the feedback control system module. So the first panel, or the first window of this software, which is also called real-time 3D-P, is the real-time 3D print panel, which just shows you the experimental setup. So if you use this software, you need to have a setup of your experimental experimental piece like this. So the scanner should be fixed on the top of the nozzle, as shown on the picture, and it will show the workpiece, how the laser beam is also affecting the printing process. And then after this, the other panel is the plot as designed panel. The plot as designed panel, when you click on the plot as designed panel, it has this blank space where it has 3 buttons: the open HTML file, plot file, and help file. So the goal of the plot as designed panel is just to plot your CAD model. So you just can open your NC code or your G code from the browser, and it can plot it for you. So I just clicked open HTML file, and then when I click and I just open it, and then when I click plot, it will plot it. If you have like any problems with the NC code file, when you click help, you can have different explanations why it's not working and how you can solve it. So this is just the initial step before the printing process. And then now you're ready, you already have your CAD model. So then you can configure the laser line scanner in the DED printer. So rather than going independently to like the DED machine and then also fixing the laser line scanner on their own different interfaces, I kind of integrate those interfaces in the software, and you can actually configure, you can write the IP address and configure and select the device for both the DED and the laser line scanner. And you can also upload the file or the NC code on the DED configuration setup. And then for both, you can start the printing process. And then like the next one is the plot as built-in panel. In this window, now you already started scanning and you already started printing. So then you'll receive frame points from the laser line scanner. So that laser line scanner need to send information or frame data points to this software where you can plot the as built-in model. So you can set up the exposure time, set up the saturation rate, number of profiles, and the idle time, and then it will overlay on the original CAD model. So as you can see, like here, the one with a curved or parabolic shape of line is the built-in model, and the as design model is the one with like the rectangular line. So then finally, you can compare and contrast your discrepancy in here, and you can decide whether to kind of quickly give remedy feedback control system to your machine. And that can be done actually by manually, or it can be done automatically. So it says the laser power, the feed rate, and the temperature are the basic parameters where we can give feedback to the machine in the laser line scanner. So you can either choose the update automatically option for all of them, or you can choose the update manually option. For update manually option, you'll have maximum threshold warning and maximum threshold error for the depths, lengths, and widths of your geometry. But if you're selecting update automatically, you don't need to do that. The software by itself will update the printing process and will achieve the best geometry as you expected from the CAD model. So from this, I can conclude that the saturation level is recommended to be 70 to 90%, and for that, 5 millisecond is the best exposure time, and 20 millimeter, which is the gap between the laser line and the nozzle, is an optimal value to achieve the best results. And always making sure that the width of reflection or the valid reflection point, setting up that valid reflection point on your printing process has huge impact on increasing the accuracy of your final printed product. And so for the height, I got 97 accuracy, whereas for the width, I got 89% accuracy. And from this, I can understand that the larger geometry discrepancy was observed on the 5-layer printed track lines. I printed 1-layer, 3-layer, and 5-layer printed lines. And from those, the more layer you have, the more error you're gonna get on your printing process, and you need to give feedback control for that. It could be either for the laser power, feed rate, and temperature, which actually shows a good agreement with the geometric quality of the final printed product. So this is my research. Those are the references I used. I do have publication papers on that. You can search it online. These are my contact information. You can email me, send me an email. You can also send me a message in LinkedIn. I'll be so happy to collaborate and also take your feedbacks.
Awesome. Thank you so much, Eden, for that presentation. Really interesting in how you're pretty much from scratch developing a monitoring and a monitoring system for me. Really well done at attempting that project. I would have run very far away from trying to do that. First question at the top of the list, I think you might have answered part of it. But the question is, what material are you working in? I imagine different materials would have different reflectivities, causing difficulties for your laser scanner. So I'm pretty sure you said you're working in 316L. Do you have any idea how you would adjust for different materials with different reflectivities?
I was using stainless steel. That was my focus. But in our lab, we can also use titanium, other metals. I would say the reflectivity would be different, but I managed the reflectivity using from the laser line scanner. So the laser line scanner automatically adjusts the reflectivity parameter. So I didn't just play with that. I just you can either turn it on or turn it off. So you can manage that automatically using the laser line scanner. But if you're using another scanner where it cannot manage the reflectivity, you would have to run a couple of trial and errors and figure out which reflectivity point is the optimal.
It's going to work best. Yeah, so I did some DED in tantalum back in the day, and tantalum glows really, really brightly for a long time after the laser has hit it. I imagine that would have a similar difficulty for the laser line scanner because it would just be getting so much input. And yeah, you might have to, I don't know, dial your thresholding down quite a lot to be able to get the right sort of measurements that you want out of that one.
Yeah, correct.
One question, we've only got 1 minute left, so I'll ask the last question for this session. What do you mean that the line scanner can detect surface defects? Is this just the height depth or a specific definition for surface defects?
So the surface defects that it can identify from, that's a good question. The laser line scanner is very powerful. I was using the German micro epsilon laser line scanner. So that it's more of bumps, it can identify the bumps and then can send you that information as a frame point, and you can extract that as a coordinate points. But for my case, I got the height and the depth information. So it didn't tell me the defect, but I can get the depth and the height from the coordinates that I receive from it, and I can just plot it on I can overlay it on my original CAD model. But for the defect, it could be the texture, roughness, or it could be some poor points or voids.
Yeah, awesome. Thank you so much. I think we're going to have to wrap up now because we've hit the top of our hour. We are heading next. If you'd like to head to the main stage next, there's going to be an hour of networking before we continue our technology track. So yeah, enjoy, grab a cup of tea, go to the bathroom if you need to, and then have a chat to some other people at the main stage. And we'll see you back in this track in an hour. Thanks very much. And thanks very much, Eden.
Sounds great. Thank you so much.